So roughly speaking, we had from 90 to 100. There were 18 people with that. 80 to 90 was roughly 16. From 70 to 80, we had 12. 60 to 70, we had 13. 50 to 60 were 6, and less than 50 was also 6. So I don't curve until the end of the course because I want to take everything into account. However, roughly speaking, 90 to 100 is an A, 80 to 90 is roughly a B, probably 60 to 80 is somewhere in the C range, and if you're below 60, right now you're getting probably 50 to 60 is a D and less than 50 is an F, is roughly speaking. Now, again, I don't curve until the end of the semester, so that's just roughly what it is looking at that. But that could change because usually the lab grades and participation grades bring your grade up, and therefore 60 is probably not going to cut it overall as a C in the class because presumably most of you will have higher scores for your labs and participation activities. Okay, the average on the coding was about 70, but the median was much higher. The median was closer to 90 on the coding. So there's a big difference between the median, which is the middle number, and the average because there was a bunch of zeros that really drove the average down. But the median was closer to a 90 on the coding, and for the paper, the average was about a 78, and I did not get the median for the paper. So I was pleased because the median was about, or the average for the paper was about 8 points higher than it was last time I taught the course. So perhaps doing some of the more interactive activities is helping, even if sometimes it may feel a bit hard to do them in class. That's a nice improvement in the score. So, as I said, I am going to go over some of the most commonly missed parts of the exam while leaving some of the less missed parts for another time. So on the questions that were fill in the blank, the only commonly missed one was the access protection you should use to declare the member function of a class that are in the class's application program or interface. So that the member functions that are in the API need to be public, because if you don't declare them public, they're unaccessible. The whole point about putting them in the API is you mean for them to be public, but a surprisingly large number of you said protected, which would make them completely inaccessible. The only thing I could think of is that many of you looked at the midterm from last time, memorized the answer, and it's wrong, okay? Because I don't ask the same question twice, okay? So in 2016, it is true, I said the access protection you would use for member variables. Well, for member variables, it is protected because you want to hide the implementation. But for the member functions, it's public. Okay, so that was the only one that was frequently missed there. Y'all did great on question 2. I was really pleased because this was one that students didn't do quite as well on the last time. The thing you had to remember is that classes go in a file with the same name as the class, not the same name as the main program. So y'all did well on 2. 3, not so much. So this was one of the most commonly missed problems. It was seeing whether you remembered what I said in class about initialization lists. So in this case, you're given 2 constructors and asked which is more efficient. And the answer is B, the one that uses initialization lists. And the reason that B is more efficient is because you only initialize each variable once. Whereas on the left, with the assignment statements, each variable gets initialized twice. And you may ask, well, wait a minute, it looks like I only see one initialization statement, one assignment statement for each of them. So why am I making the claim in A that each variable is initialized twice?
Because when it constructs the variables the first time, they don't have the value. It has to initialize them afterwards.
Very good. So it does initialize them originally using the zero argument constructor, and it assigns an empty string to each of them. So it first initializes in A, it first initializes each of those variables to the empty string by calling the zero argument constructor. Then you perform this assignment operation, thus initializing each of them twice. In contrast, when you use an initialization list, it tells C++ to avoid the zero argument constructor. It says, instead of not providing any initialization, I am telling you to call the one argument constructor, and it, in each case, assigns the argument to that variable. So fn gets assigned to first name, ln gets assigned to last name, and by providing an initialization list, we skip the zero argument constructor. So the reason B is more efficient is each variable is initialized only once rather than twice. And as I told you in class, you should get in the habit of using initialization lists for initializing objects for exactly that reason. Because if you don't use an initialization list, then C++ will initialize them using the zero argument constructor, which is a waste, because inside the constructor body, you'll probably assign another value to them. Yes, Gavin?
I kind of said something like that, but could you tell me why it was wrong?
Actually, after class. I need to kind of move along. So just come up after class and I can take a look. So other general questions. If you have a specific question about why we took points off, you can see me after class. Okay. 4, I'm not going to go over. Y'all did very well. This was one of the most gotten problems on the exam, and I was very pleased. So the issue was I wanted to see whether from the PGM labs you'd learned about your lesson about shifting pixels around, and that you had to do it from the right side rather than the left side of the vector. And almost everyone figured out that the problem was that I was starting my shift from the left side of the vector, and so I was clobbering pixels. So if I start with 10 and put it in location 3, I clobber 40. And if I start at 1 and with 20 and put it in 4, it clobbers 50. And so you end up with a vector that oddly looks repeating. In fact, essentially repeating with the first 3 values. So the solution was to shift from the right side of the vector rather than starting at the left side. And almost everyone got it. I'll just let you look at these solutions on your own. Okay. Question 5 was the hashing question. Almost all of you got separate chaining. That's definitely the easier of the two. There was some issues with quadratic probing. So I'm just going to go over the quadratic probing. So you were asked to, and I'm going to write the keys down because I'm not going to be able to see them, 12, 48, 19, 52, 58, 30, 25. And 1 second. Okay, so we're hashing these values using this hash function right here. So 32 mod 11, that's the remainder again. So 32 divided by 11 is 2 with a remainder of 10. So 32 is going to go right here. And in the table that says, what did we look at? We looked at only the bucket 10 because there was no collision. So that's 32 into here. And I know it looks like 52, so let's make it 32. Then we hash 12. 12 divided by 11 is 1 with a remainder of 1. So 12 goes in there, and we end up looking at bucket 1 for 12. Then 48 mod 11 is 4 with a remainder of 4. So 48 goes here, and we look only at bucket 4. Okay, then 19 mod 11 is 8. So we look only at 8. And now the fun begins. So 52 mod 11 is what? Eight. 52 mod 11 is 8 because the quotient is 4 and the remainder is 8. So we want to put 52 into bucket 8, but that's a collision. So using quadratic probing, we look at the initial value of the hash key, and then we do I squared for I equals 0, 1, 2, 3. So the first one is 1 squared. 8 plus 1 is 9. We look at location 9, and lo and behold, we can put 52 there. Now we look at 58. 58 divided by 11 is 5 with a remainder of 3. So 58 goes here. Now we look at 30. 30 mod 11 is 8. So we look at bucket 8. No good because there's already a value there. Then we look at 9, but there's already a value there. Then we look at 8 plus 2 squared, which is 4, which is 12. So we look at bucket 1, but there's already something there. So now we look at 8 plus 3 squared, which is 17. 17 mod 11 is 6, and 30 finds a happy home finally at bucket 6. And finally, 25 mod 11 is 3. And unfortunately, well, of course, by the end I was going to be doing this to you. Bucket 3 is full. So now we look at 3 plus 1 squared. But bucket 4 is full. So we look at 3 plus 2 squared, which is 7. And 25 finds a happy home. So we looked at 3, 4, and 7. And hopefully, because I did not actually, I did this without looking at my solutions, make sure I did not muck this up in any way. Nope, it is all good. Okay, so this is what you would put into the hash table, and then down here you would have put, for example, for key 10, 10, or for 19 you would put 8. For 30, where we did a lot of searches, you would have put 8, 9, 1, and 6, like that. Okay? So that was quadratic probing. That was kind of a medium difficulty problem, it turned out. Questions on that one? Okay. The bit hashing, you all did much better than I anticipated. I was very happy about that. I am going to let you all look at my solutions. If anyone has a question, though, I'm happy to answer it. Okay. 7, I'm just going to go over briefly because there was a little bit of misunderstanding there. So actually, let me show you the answer. We can take it from there. Okay, so 7, what you had to do was do character arithmetic. You were told that you were searching a maze collecting animals, and the only difference really between this problem and lab 0.5 was that each letter was worth 2 points rather than in effect 1. So effectively you were using the same formula that you used in lab 0.5. You were doing character arithmetic, so you had to find in effect the offset from A, which is animal minus A will give you the offset from A. Now that will give you 0 for A, 1 for B, and that's not quite what we want because we can see A stands actually for 1 or 2 points, B stands for 4. So after getting the offset, we have to add 1 to that. And then we multiply each of them, in effect is worth 2 times its offset. So that's how we came to that. Okay, and this is apropos because in lab 5 with the bit matrices, you are also doing character arithmetic. Okay, Dr. Planck is representing the elements of the matrix with characters rather than with integers. Does anyone know why he might be torturing you with characters rather than integers? And part of it is, yes, we want you to get, again, more familiar with character arithmetic, but there is another reason why he's using characters rather than integers in those matrices. Think about storage. What could there be about storage that...
Char is 1 byte and is 4 bytes.
Very good. A char is 1 byte and an integer is 4 bytes. And in his research, some of these matrices become enormous. And the integer storage would be 4 times greater than the character storage. Now, because it's 0 and 1, I believe that actually in his research he does some clever stuff where he's actually using bits, which take up only 1 bit. You can actually jam 8 of those into a byte. But for both reasons, storage purposes and because he wanted you to get more experience with character arithmetic, he's storing the numbers 0 and 1 as characters in his bit matrices. If he really wanted to be mean, he could have used bools. And that would have been really efficient because a bool is 1 bit. Okay. Question 8. Hopefully, if you missed this problem on the coding question on Wednesday, you went back to your notes to make sure that you knew why your code was incapable of printing out C++ strings using printf. I had a bunch of people on the coding exam forget that you need to use that printf cannot print C++ style strings, that to print a C++ style string, you need to call the C_str function. So that was the only real trick to putting it in a field 15 characters wide. Then I said the salary should be left justified. So salary is left justified in a field of 12 characters with 1 decimal digit. So left justification is a minus. By the way, some of you tried to use plus for right justification. There is no plus. That'll get you a compiler error message. By default, printf uses right justification, so there's no reason to put a plus there. And C++ doesn't buy it. It actually gives you an error message if you put a plus. So only use a minus for left justification. Then the field width is 12. Then the period indicates that there's going to be some number of decimal digits after that period, and it is 1. It also tells printf that we're using fixed notation rather than scientific notation. Remember, with cout, you had to specify either fixed or by default it's scientific notation. With printf, the reason it knows you want to use fixed notation is because of the dot there, followed by the 1. And then age is left justified in a field of 6 characters, so that's minus 6d. The big issues here were with left justification and with forgetting that you have to call the C_string function in order to print a C++ style string. And finally, the killer. Number 9, missed by, yes.
We have a question about, say, question number 8.
Mm-hmm.
For the integer age, can we use instead of d, but the character I?
Yes, if you were counted off for using I will give you points back. Okay, yes, you could have used I rather than D. If you got points taken off, I'll give them back for that. Okay. Other questions about 8? Okay, 9 was easily, actually, the constructor question in 9 competed for the most frequently missed problem on the exam. So this was meant to test your ability to read code and not just simply make assumptions. And it looked like, looking at many of the answers, many of you were making assumptions. And the second thing that came out of it was that most of you are still confused about the difference between standard input and command line arguments, which this problem was also designed to test. So what the code was meant to do was distinguish between words, integers, and floating point numbers. And it was simply printing out the words in the order they appeared. It was summing up the integers, and it was summing up the floating point numbers. So the way it was doing that was it was reading from CN. Now the first thing you should notice is up here, main. What do we notice about that declaration? There's nothing about command line arguments. So we are ignoring the command line arguments. So 10 in Mario is just a head fake. It is designed to see whether you know that those are command line arguments and not standard input. They're not. Anything that appears on a command line is a command line argument. It is not standard input. So anything on a command line, that's why they're called command line argument, are parameters to main. And main is free to disregard them, as main did here. So main completely disregarded the command line arguments. Okay, all it cared about was cin, and we catted out input.txt, and then we redirected standard in to input.txt. So really your input started with 3.6. So cin read each value into input, which was a string, so it was guaranteed to work. Cin should always work when it's reading input into a string as long as there's some input to read. Then we need to check whether it's a number or a string, and that's what I was doing here. I stuffed it into a buffer, which was a iString stream, and I tried to read it into num1, which I declared as a double. If that was successful, I wanted to know whether the number was an integer or if it was a floating point number. And the way I determined that was I did a find on the string, and I checked to see whether it was a dot in that string. If there was a dot in the string, then I knew that it was a double. If there was no dot, which means string no position is returned by find, I know it's an integer. So in that case, you see that I cleared the buffer, stuffed input back into it a second time. Here I did it a first time. But in order to read from it a second time, I had to clear the buffer and stuff it back in. And then I read that string into an integer and did my summation. Okay? And same thing with doubles. I summed them up. If this attempt to read it into a number failed, then I immediately printed out the input. So what happened is I first printed out every word in the file. So the input included Brad, Smiley, Jill, and Nancy. So those were the first 4 things to be output because they were all words. And then at the end, I printed out sum1 and sum2. So sum1 was the sum of the integers, and the integers were minus 5 and 50. So sum1 was 45, and sum2 was the sum of 3.6, 14.5, 20 because it has a dot in it. That makes it a floating point number according to this definition of it. And 17.4. And don't tell me you can't do this calculation in your head. I was very nice to you. 17.4 and 3.6 very nicely add to 21. 14.5 and 21 is 35.5. And adding 20 to that, you get 55.5. Okay, if you miss this and you claim you need a calculator, I am not sympathetic. Okay, you need to be able to do this one in your head or on paper. So questions about this, because this easily, other than the constructor one, was the one that killed the largest percentage of you. Yes?
So about number 90, like the other solution to it, like.
Yeah, we gave you credit because, so it was an HTML error. You'll notice on your original test that there's 2 missing, that it says include blank. There was an HTML error. I didn't use entity codes, and I never caught it in proofreading. So you and one other student, Julian, did that. You got full credit. Okay, because I felt it was my fault for not proofreading it. Okay, but fortunately everyone else did not see that typo and went through and did it the way we wanted. Okay, you probably won't get that benefit on either of the other 2 ones because I will be here. And you probably, when something funny like that occurs, you need to ask a question. Since the TA was proctoring, I gave you the benefit of the doubt. But probably when you see something funny like that, that's probably a typo. It's probably not what I intended. Okay? So I will be here for the midterm and the final, and you will not get credit if I'm here. So just a word of warning. Other questions? Yes.
I have explain again about a string, colon, and POS.
Yes. So right here, the find function needs to return something. So it returns the index of the first location where that period appears in the string. But if the period does not appear in the string, it needs to return some other value indicating that that period was not found. And in this case, the string library defines a constant called string : NPOS. So string : is simply the prefix for the string library. When you include string, that includes the NPOS constant. NPOS is a constant. You don't know what its integer value is, and it varies actually from compiler to compiler. Compilers are free to give it any value they wish. Most commonly, it would probably be -1, but there's no guarantee it's -1. And that's why you have to refer to it as string : NPOS. So the string : says that this constant is defined in the string library, and then NPOS is the name of that constant. And it stands for no position. So it stands for no position, meaning that there is no place in the string where the period appears. Okay. Other questions about this problem? Okay. So then, you actually did quite well on the coding questions, and I don't have a ton of things to say actually about the coding questions. I'll let you look at the answers. First of all, I guess I will say that I have an annoying tendency on exams to have one of the problems be closely related to something from the notes. So from the sample midterm, I had showed the first one, Moonglow, in class, and this tail problem comes from Dr. Planck's notes. Okay, so it was simply seeing whether you knew how to push things onto a vector and then adjust the number of lines to print if necessary, and also was designed to check if you remembered how to convert command line arguments to integers using input streams. And some of you tried to use A to I even though I told you you couldn't, and you got dinged because of that. You needed to use I string streams here. And I got a fair number of students saying I forget how to put a string into an I string stream. And that blew me away because you had a one-page cheat sheet. And not only did you have a one-page cheat sheet, but it was pretty clear, I thought, from the sample midterm that string streams would be on this coding. I mean, that was one of the big emphasis points of the first third of this course was string streams. So when I give you a one-page cheat sheet like that, stuff like this you really need to have on it. Okay? So I wasn't particularly sympathetic. You lost a bunch of points, like 2 to 3 points, for not remembering how to stuff something into a string stream. And then most of you got this part about how to adjust the line. I was really pleased about that. So a bunch of different ways to adjust, even adjusted my solution based on it because I felt this was even nicer than the way Dr. Planck did it. So some of you did it that way, and I did it that way as well. Again, I'm not really going to go over it because most of you got it. 2 was definitely more problematic. You were being given a string which represented team members and being first asked to break that string into individual team members and add it to a 2D vector, and then you're being asked to find a team leader and print that team leader's team members and do it in a nicely formatted way. So more of you got read teams, but there was still some issues. Many of you thought that group.size somehow returned the number of words in group. It doesn't. What does group.size return? Pardon?
The size of the string.
The size of the string in what? Words or characters? It's actually the size of the string in characters, not the size of the string in words. And some of you tried to pull this string apart by going through it character by character and looking for blank spaces. No, don't do that. String streams, that's what they're there for, to break a string into its constituent parts. And you first add the team members to a vector. And you could either, I chose to define a new vector and then first add the team members to that new vector. And then once I had finished adding the team members to that vector, which I called row, I then added the row to the end of the 2D vector. Some of you instead first resized teams. You said teams was teams.size plus 1, which is fine, so that resizes it. And then you push back, instead of saying row.pushback, you said teams of, well, the best way to say it was original rows equal teams.size. And then you've saved that, and so it's really now original rows is now the last index dot pushback. And that worked just fine too. In fact, I used to think that this way was faster, to do the resize and then to push onto the last row. But it actually turns out my solution is faster. I've coded up both and done it with really large vectors. It turns out that for some reason, pushback is just faster than resize. And so on some of your solutions, I said, look, you got to use pushback, not resize, because pushback is faster and it's also simpler to read. Now, I didn't do it with this problem because I thought it was perfectly reasonable to resize the back of the teams first and then add it. But some of you did, inside of here, you would say, instead of using pushback, you would instead say row.resize, row.size plus 1, and then you would say row.size, new size, minus 1 equals, and that's just hard to read and it's just not efficient. So you did get a comment there about that not being the best way to do it. Use pushback, that's what it's there for. And then print team, the big issue here, some of you searched the entire 2D vector for the team leader when I told you the team leader could only be the first name of the team. So some of you would search every single entry, and if I gave you something that wasn't a team leader but a member of a team, you would still return true, and that wasn't good. You only search the first column of each row. That's where the team leader is. And then there was a lot of different ways that people put things into columns, but I was impressed. People did it right. Some of you used mod. Some of you used a counter. I'm perfectly down with you using a counter, going 0, 1, 2, or 1, 2, 3. It's a perfectly acceptable way to do it. In fact, it's probably easier to read. You should at least be able to read this mod idiom. So that is the way I did it, to put them in rows of 3 each. The reason for names plus 1 here is because if num names is 0, I don't want to print a new line character before my first line. And most of you figured out it was no good to put a new line character before the first line. Some of you said if nums names mod 3 and num names not equals 0. Perfectly fine. Perfectly happy with that. Okay, some of you, as I said, used a counter, counting column 1, column 2, column 3, and when it got to column 3, you printed a new line character and you reset it to 0 or 1. Perfect. Nicely done. Okay? And some of you forgot to print out either no team is found, or some of you put this check for no team inside of your for loop. That's not good. You don't know until the end of the for loop whether you found the team leader or not. So constantly checking inside the for loop to see whether the team leader has not yet been found and whether you should print out the message because you've now reached the end of the loop is counterproductive. Just wait until the loop is ended and do the check once at the very end. In fact, you notice I don't even protect my printf statement here with an if. And the reason I don't protect it with an if is because if I found the team leader, I'd already returned. So I couldn't even get to out of my for loop unless I had not found the team leader. Now, a couple minor things on efficiency. One, some of you continue to search the for loop even after you found a team leader. Don't do that. As soon as you find a team leader, get out of the loop. It's a waste of time to keep searching. You found it. Okay? Second thing, some of you are getting in the bad habit of using ints for binary valued variables. You'd have int flag. Use a bool. That's what it's there for. When you have a binary valued variable that's essentially true false, use a bool. Okay? For one thing, the compiler can combine multiple bools into one variable or one 8-byte chunk if it wants, so it's more efficient. But two, your code is more readable. Boolean variables are true false. They should be declared as bools. Okay? So, if you have questions, I would say see me after class because I do want to spend a few minutes introducing today's topic. And there's not going to be a class exercise today because there's just not enough time. So, there will be going back to class exercises on Thursday. So, we want to start talking about a new data structure. We've talked about hash tables. Now we're going to, and you've already learned about vectors and arrays. The next thing we're going to talk about is something called lists. Okay, and you're familiar with lists. You make a grocery list. You make a to-do list. Okay, you are familiar with making lists of things. Okay, so it's a very, common concept. And we're also going to show you why lists are better than vectors at doing certain things. And then we're going to show you something called doubly ended queues, which we won't get to until Thursday, nor will we get to bad vector usage until Thursday. Okay? So, a list, as I said, is just a list of things, like a grocery list. Okay, it's an unordered list of things. Or when you see your email, that's kind of a list. It's a list of all of your emails. Or text messages, that's a list of all of your text messages. Okay, so conceptually, it's just a list of things. And we talked about how we want to be able to do find, insert, and delete efficiently. Okay, it turns out that lists are not particularly efficient for find operations. Okay, usually lists are unordered. If you really need something ordered, there's better data structures for keeping things ordered. Okay, now insert, it is very efficient. Okay, and we'll get to that later in the semester, but basically, find you're going to search the entire list, and that's not too good. So I'm going to say that's bad. But insert typically can be done with one operation. That's good. And delete can typically be done with one operation in effect, and that's good. We will see why in a moment. So insert and delete tend to be pretty efficient in a list. Find tends to be an abomination. Okay. And it turns out that you don't use lists particularly often. Usually you use some other data structure simply because the find is such a bad price to pay. But they can be useful at times. So a list is part of something that is called the STL, which stands for Standard Template Library. You are going to become intimately familiar with the Standard Template Library. It provides a whole slew of data structures. Okay, it turns out that hash tables have not been included in the Standard Template Library until very recently. But lists are in the Standard Template Library, and the Standard Template Library defines a series of methods. Push front adds something to the front of a list. So if I have something like, say, groceries, and I have oranges and apples already on my list, and I say push front grapes, then it puts grapes at the front of the list. So that's what push front does. It adds something to the front of the list. And Dr. Planck uses push front to reverse a file. So if I have a file that consists of, say, oranges, apples, grapes, watermelon, then what this code does, it reads oranges, adds it to the list. Then it reads apples with getLine, and the push front adds apples to the front of the list. Then we read grapes and add it to the front of the list. And finally, we add watermelon and add it to the front of the list. And you can see what we've done is reverse the list. Kind of neat. So then he prints it out using what looks like Greek right now to you. Okay, these things that he has right here are called iterators. Okay, you've seen them before. When you say I++, you're in effect iterating through a vector with an index. Here we're iterating through the items of the list. So lit is called a iterator because you're iterating through a list. And you see lines.begin, that returns the first element in the list. Lines.end denotes the end of the list. And lit++ advances us to the next element in the list. So what happens, let's go back, we have watermelon, grapes, apples, and oranges. In fact, what you don't see is two additional elements of this list, which I'm going to indicate with X's, and they are called sentinel values, because they guard the list, just like sentinels in the olden days guarded the fort or a city or a house. These things guard the list. So they are a value that is, quote, not part of the list, but yet guards the list. There's one at the beginning of the list and one at the end of the list. You don't really see them. You don't know they're there, but the standard template library puts them there. When you say lit equal line spot begin, it makes lit point to the first element, which is watermelon. When you say lines.end, what you're actually getting is a pointer to the sentinel value, which denotes the end of the list. So this sentinel value denotes the front. This sentinel value denotes the end of the list. So when you say lines.begin, you actually don't get front. You actually get the first element of the list, which is watermelon. And the way you access it is through the star. It's like you're dereferencing a pointer. And it returns the value to which that iterator points, which in this case is watermelon. Then when we say lit plus plus, it increments lit so that it points to the next element in the list. And again, the star lit will dereference it and print out grapes. Then we advance lit using lit plus plus. It goes to apples. Then it goes to oranges. And finally, when we advance it, it goes to the sentinel value and points at the sentinel value, at which point it becomes equal to lines.end. And at that point, we terminate the loop. Okay, so it's a pretty simple thing, but there's some multiple things going on here. You're learning about lists for the first time. You see that the way you declare a list is list, and then the type of element that the list is storing. You also have to include list. So up there we have an include statement for list. Okay, and then the way we iterate through the elements of the list is to use an iterator. And you can see that we append : iterator to the type of data structure that we're iterating through. You'll see that iterators are ubiquitous in the standard template library. So you always indicate what type of data structure you're iterating through by prepending the type of the data structure. Okay, and then as we said, lines.begin, points to the first item of the list, whereas end actually points to the sentinel value at the end of the list. Lit plus plus advances the iterator to the next item in the list. Star lit dereferences the iterator and allows you to look at its value, the value to which it's pointing. So questions about that? Okay. So we can also iterate in reverse through a list. So here we're actually adding, using the pushback command to add items to the end of the list. So again, if we had oranges, apples, grapes, and watermelon, now pushback adds to the back of the list. So initially the list is empty, so we have oranges. Then when we read apples, pushback adds it to the end of the list, just like pushback does for a vector. Then we add grapes to the end of the list, and then watermelon to the end of the list. And again, there's sentinel values here. So when we use this reverse iterator, where we put an R in front of it, and notice here, when we declared it, we said we want a reverse iterator. What do you think lines.rbegin returns a pointer to? Not the sentinel. Begin never returns a pointer to the sentinel. It returns a pointer to the watermelon, the first element that it is supposed to point to. Now, because we're going in reverse, we start at the back of the list. Now, do you think this makes sense? I don't. What do you think I think would make more sense? Minus minus. But that's not the way of the standard template library. So even when you're going in reverse, you increment the iterator, and that makes it go to the next item in reverse. Notice we put an R in front of these puppies, so to indicate we're going in reverse too. And when we R end, actually returns this sentinel value right here. This is what R.end returns. So you can also iterate through lists in reverse. Okay? Now, this isn't really handy. You say, wait a minute, it's nice to be able to add something to the front of a list, and it's nice to be able to add something to the back of the list. You're absolutely right. But if you're adding something always to the back, it's much more efficient to use a vector, because you can get directly to the item you want in a vector with an index. And it's going to turn out that if all you want to do is add to either the front or the back, then double-ended queues are going to be more efficient. So you might just be wondering, okay, Dr. van der Zanden just spent 10 minutes going over that. What are lists good for? Well, they're good for inserting into the middle and deleting in the middle. And for that, they are better than a vector or a double-ended queue. So for example, sometimes you've got your grocery list and you got it organized by sections in the grocery store, and then you remember another fruit you want to pick up, so you want to insert it in the middle of the list. Or as you go through your grocery list and you get items, you may cross them out, which is deletion in the middle. So lists are really good when you need to insert or delete from the middle of the list. When you want to insert or delete from the middle of the list. Okay? So, let me show you that. So let's say we have the list oranges, bananas, milk, and orange juice. And we want to insert yogurt before milk. So yogurt's supposed to go right here, right before milk. Okay? Well, there's a way to do that. So here's a function. We're inserting this new item. This is the target. So in this case, new item is yogurt. And the target is milk. And we're inserting into this list, and notice the reference variable because we want to modify the list. We're always pass our objects by reference. So the first thing we're going to have to do is find our target. So we're going to need to iterate through our list to find the target. So that's a linear search. You should be familiar with linear searches. You've done them a lot. So we're just iterating through the elements of the list using this for loop. And we're checking to see if the value of the iterator is equal to our target. If it is, there's an insert command. And the insert command takes an iterator and it inserts the new item before the iterator. So insert inserts new item before the item pointed to by the iterator. So that's what insert does. And notice I say break right after that to get me out of there, because why do I break at this point? Why not just continue on? because I already inserted and I'm done. No reason to continue, so I break. If you like to use a flag there and say found equals true, and then say lit not equal grocery list dot end or found equals true, or I say and found equals false, fine. I'm fine if you like flags. Dr. Plank hates break. I love break. So these are actually my notes right here. I added them. That's why you never see break in Dr. Plank's notes. But I like break. Okay, if I get to this point, I want to check to see if I reached the end of the grocery list without finding the item. And if I did, then lit will be equal to grocery list dot end. In that case, I do a pushback because I still want to add the item to the list. Okay. Questions about that? One last thing and we'll be done. We can also delete items from the middle of the list. Okay, so in this case, actually, you know what? I'm going to save this for next time because I think this is worth taking about 5 minutes to go through. So next time, we'll pick it up with deleting items from the middle of the list. We'll also go over abstract data types, double-ended queues, and why it's bad to delete or insert from somewhere in the middle of a vector.
Could you scroll up 1 second?